Okay, quick review of linear algebra, matrix algebra. So we can take a system of equations and we can write it in matrix form. And the solution to the system is x is 2 and y is 1. You could just check that by inspection. But we're going to explore and review the matrix solution to these. So what we've got here in matrix terms is we've got an equation that looks like A, where A is a matrix, U, where U is a vector, whose components are x and y, equals B, which is another vector, 7, 0. And the way to go from this matrix statement back to the actual equations is matrix multiplication. And the algorithm for matrix multiplication is you multiply across rows in the first matrix or vector and down columns in the second. So we would multiply 2 times 3 plus 4 times 2, which of course is 14. And that would be the first element of our answer. And then we would multiply 1 times 3 plus 1 times minus 2, or rather plus minus 1 times 2, and that equals 1. So we notice for multiplication that there's 2 rows by 2 columns, and then this is 2 columns by 1 row. And it's essential that these two be the same in order to multiply. So these must be the same in order to multiply these matrices together. And then this tells you what the answer will be. It'll be a 2 by 1. So it's now 2 rows by 1 column. Okay, so for instance, we've already multiplied that one. Here's another example to multiply these two together. So this one is algebraic, so it'll be a11b1 plus a12b2. So we multiply across rows here and down the column. And here it's going to be a21 times b1 plus a22 times b2. And again, this was a 2 by 2 matrix, and this was a 2 by 1. Those are the same, and so the answer ends up being a 2 by 1. 2 rows in 1 column. Now those were examples multiplying a matrix by a vector. You can also multiply matrix by matrix. So here, you multiply across rows. So across the first row, down the first column, is 2 times 3 plus 4 times 2, so that's 14. Then across the first row and down the second column is 2 minus 8, that's negative 6. Then across the first row and down this column, 1 times 3 minus 1 times 2, that's 1. Then across the second row and down the second column is 1 plus 2 is 3. So again, this is a 2 by 2. This is a 2 by 2. Those have to be the same, and the answer ends up being a 2 by 2. Now, important definition, the identity matrix has got 1s on the diagonal and 0s elsewhere. And we notice that if you take any matrix, and if you multiply it by the identity matrix, then you get back the original matrix. So multiplying across the first row and down the first column, then multiplying across the first row and down the second column. Here we go, second row, first column gives us a21, and second row and second column gives us a22, which is exactly the original matrix. So this identity matrix is kind of like the 1, right? Multiplying by 1 gives you itself. It's the 1 for matrix multiplication. And it's also true that if you multiply the identity matrix by a vector, it gives you back a vector. Now back to our system of equations. We need to be able to multiply by an inverse in order to solve a system of equations. This is similar to, equation solving. We would divide, if we had like 4x equals 3, we would divide both sides by 4 in order to solve the equation for x. Well, this is essentially multiplying by the inverse of 4. So let's just go back to the first page. Let's cross this out. I want to say this is a times u equals v, where these are vectors. So yes, so here we've got a times u equals v for our equation. And that means, so this is the coefficient matrix here. This is the unknown, and then this is a vector of numbers. So in order to find u, we're going to pre-multiply by the inverse. We have to do that on both sides. And then A times A inverse is the identity matrix, and the identity matrix times u is just u. So this is going to give us a solution for the unknown. So this is the coefficient matrix. This is our unknown, and this is a known vector. It was what was on the other side of the equal sign. So we could solve a system of equations if we can invert a matrix. Now, we're going to restrict our attention to a very simple case of just a 2 by 2 matrix. And for a 2 by 2 matrix, A, B, C, D, you could show that this is the inverse. D minus B minus C minus A divided by this. And you're going to show that in an assignment, and the way you're going to prove it is just to show that if you multiply the matrix A by the matrix A inverse in either order, you get the identity matrix. So let's use that inverse formula now to solve this equation. Remember, we had something of the form A times U equals V, and we were saying that by pre-multiplying both sides by the inverse, that we could solve the equation. Well, let's find the inverse of matrix A. So A, the A matrix again, is 2, 3, minus 1, 2. And that's of the form A, B, C, D. And we saw that the inverse was the number, AD minus BC. So that's 4 minus minus 3, that's 1/7. And then you switch D and A and negate them. And then you keep B where it is and negate it, and then keep C where it is and negate it. So that is the inverse matrix. So now we can use that to solve the system, because if A times U is V, then pre-multiplying by A inverse on both sides, I get U is A inverse of V. So U was the unknown. It's a vector with X and Y component. A inverse is what we just worked out above. We can write it there. And then V was the known answer vector, 7 and 0. So it remains to multiply this out. So multiplying across the top, we get negative 14 and 0. And then multiplying across the bottom, we get 7. Then dividing by 7, we get negative 2, 1, which is exactly the solution to the system. Sorry, a little mistake there. Yes, this should have been just positive 2. So this is positive 2, because the inverse formula that we had, you just switch the location of D and A. You don't make one negative. So that was, my notes had a mistake in them. So these are positive. So this is positive 14. And then we end up with an answer of positive 2 and 1, which we said earlier was the solution to the system. So this inversion process works. And you know that because you've done linear algebra already. So matrices can be used to represent systems of equations and solve systems of equations. And you can do one, just as a simple example, a 2 by 2 system in your assignment. But that's not all matrices are good for. Matrices are also can represent transformations. An important transformation in physics is a coordinate rotation. So rotating from, say, an x, y coordinate system to an x prime, y prime coordinate system. And this can be accomplished through something known as a rotation matrix, which has the form cosine, cosine, sine, minus sine on the main diagonal. And you're going to show in an assignment that the same point, P, which has coordinates x and y, in the prime coordinate system, if you project it down, the x prime and the y prime are going to be given by this matrix times the x and y. You're going to prove that in an assignment. So that's a second application of matrices. A third is the eigenvalue problem, and this is of great interest in physics. Now, eigenvalues are just vectors that aren't rotated or twisted at all when they're transformed. Instead, they're just stretched or squashed by some factor, lambda. So a vector that is, in a sense, direction invariant under a transformation is known as an eigenvector. So we're going to show that for this matrix, which is a symmetric matrix, that both of these vectors are eigenvectors. Now that means that we have to multiply the matrix A, which is this one, by this first vector, and we should get a constant times that same vector. So let's just divide the page in half here. And then we'll do the first vector on this side. So if we multiply the matrix A, which has the form A, B, B, A, by this vector, 1 over root 2, 1 over root 2, do we get some constant? So does it equal some constant times the same vector? Okay, clearly I need a finer point here. So let's do the matrix multiplication. So it's going to be A times 1 over root 1/2 plus B times root of 1 1/2. So that's A plus B times 1 over root 1/2. And then this just works out to be the same thing because it's B times 1 over root 2 plus A times 1 over root 2. And we see that this, of course, is just A plus B times our vector. So it is indeed true that this matrix multiplied by this vector is a constant, and the constant is A plus B. So let's check next if this is an eigenvector for this matrix. Does the matrix A times the vector V2, does it equal some constant times the vector? So again, A, B, B, A times this vector here, minus 1 over root 2, 1 over root 2. Does that equal a constant times the same vector? Okay, so let's do the matrix multiplication. So here we're going to get negative A plus B, or another way to write it is A minus B times negative 1 over root 2. And then here we're going to have minus B and plus A, or that's going to be A minus B times 1 over root 2. But that, of course, is A minus B times minus 1 over root 2 times plus 1 over root 2. So again, multiplying this matrix by this vector equals a constant times the vector. So yes, this is an eigenvector, and this is the corresponding eigenvalue. So why are we doing this? Well, we're doing this because we can use matrices to solve, say, simple harmonic motion problems, and ultimately to solve coupled oscillator problems, because the eigenvalue problem is the same as solving these equations. So we solved this differential equation before. How on earth are matrices involved? Well, sum of the forces is ma, so the force is the elastic force, and the acceleration is the second derivative of position. So we rewrite that as x double dot is minus k over mx. Now we can, and of course we introduce omega naught squared as the root of k over m. Now, we can write those equations in the following form. We could say x dot, the derivative of x, well, that's certainly just x dot with nothing x. And then x double dot, our equation here, is nothing x dot minus omega naught squared times x, which we write in matrix form like this, because 0x, 1x dot, minus omega naught squared x, and 0x dot. That's missing an omega naught there. And then this is a coefficient matrix, A times x, x dot. So we've written x dot and x double dot as a vector on this side, but of course that is a derivative. We can write x dot and x double dot as the time derivative of x, x dot. And then what we had on the other side was that coefficient matrix A times x, x dot. So now we have a differential equation involving vectors. The time derivative of some vector u is itself times the vector. So here's the ddt of u, which is u dot, is a times u. So this is now a differential equation, but it's a differential equation involving vectors and matrices. Now, this says the derivative of something is itself times a constant a. Well, which function is its own derivative? Well, an exponential function. So let's try something of this form. U is some vector times this e to the lambda t, this time-dependent function. So this is not a vector, but v is a vector. So if we substitute that in, then we do the ddt of this, and the time derivative of u, du dt, where u is a vector. You time differentiate this side. V is assumed to be a constant vector, and then you time differentiate this, and that will be e to the lambda t times lambda. So then on this side, you've got v e to the lambda t times lambda, and then on this side, you've got a times u, but we were letting u be v e to the lambda t. So the e to the lambda t just disappears, and you can see, holy smokes, a times this unknown v has to be lambda, a constant, times that unknown v, i.e., this thing will be a solution provided v is an eigenvector and lambda is an eigenvalue. So the simple harmonic oscillator has been reduced to an eigenvalue problem. Now, the matrix that we've got, and we wrote it on the previous page for A had the form, it's sort of an anti-symmetric matrix. It was, sorry, not symmetric at all. It was something like this. And so it's got the form where the entries on the main diagonal are the same, and then the ones off the main diagonal aren't. Now, in an exercise, we showed that the eigenvectors for this matrix had this form here. And so let's see what they are for this particular A in terms of omega naught and 1. So it is 1, and then C over B. C is minus omega naught squared. So this is the root of minus omega naught squared. So that's the second entry in the eigenvector. Well, the root of omega naught squared is just omega naught, and the root of minus 1 is I. So this is a complex eigenvector. Same thing here. This is going to be, so C over B is minus omega naught squared over 1, or just minus omega naught squared. The root of omega naught squared is just omega naught, and then the root of minus 1 is just I. Excuse me. So these are the eigenvectors for this matrix A, and the eigenvectors tell us the solution to the equation for simple harmonic motion. Now, we already know what that is, but we're just going through it here using matrix techniques. We're solving a problem where we already know the answer just to make sure it agrees with what we expect. So what are the corresponding eigenvalues? Well, the eigenvalue problem is solved as follows. Whoops, one too many equal signs there. So a vector v is an eigenvector if the matrix times the eigenvector is a constant times the vector itself. So we know what the matrix is. It's the coefficient matrix. We changed our simple harmonic motion differential equation into this matrix equation. So we're going to take that and multiply it by the first eigenvector, which was the 1I omega naught, and then see what we get. Well, multiplying across the first row and down the first column, we get I omega naught. Multiplying across the second row and down the first column, we get minus omega naught squared. Now, that should be equal to some constant times this same vector. And we see what the constant is going to be. It is I omega naught, because I omega naught times 1 clearly is I omega naught. And if you multiply this by I omega naught, you get I squared, which is minus 1, and omega naught squared. So this is the first eigenvalue corresponding to this eigenvector. Let's find the second one. So here is the matrix of coefficients that correspond to our differential equation. And then this is the second eigenvector, minus I omega naught, sorry. So multiplying here, we get minus I omega naught. And then here we get minus omega naught squared. And now we ask the question, what would the second eigenvalue be? Well, we see it's, oh, that's horrible, that's supposed to be equals. We see that it is minus I omega naught. And that's not supposed to be a bar, that's not supposed to be a fraction at all. That's just the second element in the vector. So there's the first element, there's the second. So if we multiply minus I omega naught by 1, we do indeed get that. If we multiply minus I omega naught here, minus times minus is plus, I times I squared is negative 1, omega naught times omega naught is indeed omega naught squared. So those are the two eigenvalues. So what have we shown here? Because again, we know what the answer to this problem is. Well, we've shown that the solution to the equation has the form a vector, an eigenvector, times e to the lambda t, where this is lambda. Now, that's e to the I omega naught t, which is exactly how we solved the equation earlier. We tried a solution to the form e to the I omega naught t and found that it worked. So we can write the solution to this equation in terms of the two eigenvectors and the eigenvalues. So there's a constant times the first eigenvector times e to the first eigenvalue t, plus a constant times the second eigenvector times e to the lambda 2t. So if we put that in there, so it's a constant. Remember, this eigenvector was 1 I omega naught, and then the first eigenvalue was I omega naught. The second eigenvector is I omega naught, and then this was minus I omega naught t. So the first element, the top element, gives us the position x. The second element gives us x dot, the velocity. So reading off x, we get c1 e to the I omega naught t plus c2 e to the minus I omega naught t, which of course is exactly the solution we found before, and we saw that we could write it in the more common form a cos omega t plus delta, or a cos omega t plus b sine omega t. And I guess those really aren't a and b because it's not the same as that a. So I think I use something like, maybe I use d, maybe I use d1 and d2. So by writing the equation for simple harmonic motion in matrix form in terms of this vector u, we found that u dot was equal to au. And then we said, yes, these things, Then we said, yes, these things are matrices, but we know how to solve this equation already. It must be that u is an exponential function of time times some constant. And u and v are vectors. A is a matrix. Just a single time derivative there. But it must work in the same way. We must be able to write it as some function. And then we said, yes, this is really an answer provided v is an eigenvector and lambda is an eigenvalue. Now, these eigenvectors, we have another word for them in physics. They are called the normal modes of the system. So for our simple harmonic oscillator, these end up being the normal modes. And we'll interpret them a little bit when we get together. But there's an important significance of this vector and also this one that we can talk about. And so the eigenvector problem ends up being a really important one in physics, and these normal modes have a physical interpretation that's important, and it comes up in solid-state physics, it comes up in quantum mechanics, it comes up again and again, and that's why we're introducing it in this course in intermediate mechanics. So when we meet, we're going to look at a different problem, one that we haven't solved before, and we're going to write it in its matrix form, see that the solution again has to do with eigenvalues and eigenvectors, and that those are normal modes, and that once again we'll interpret what the normal modes tell us physically.